You type one sentence into a chat box. Explain why the sky is blue in one sentence. Then you press send. A moment later, an answer begins to appear. We often summarize everything that happened in between with one sentence. A large language model predicts the next token. That sentence is correct. But it leaves out almost the entire mechanism. It does not tell us what entered the model, how letters became numbers, which matrices acted on those numbers, or what attention calculated. It also leaves unexplained where the next token probabilities came from and why the process had to run again after one token was selected. In this lesson, we will follow this request all the way through the system. We will begin with the text you can see. We will turn it into token IDs, then vectors, then a matrix of context-dependent representations. We will open one transformer block and calculate attention step by step. We will follow the final vector into a probability distribution over the vocabulary. Then we will watch one token get selected, added to the sequence, and sent through the loop again. After that, we will rewind. We will ask where all of those matrices came from and see how next token training changed them. This is not a reconstruction of ChatGPT, Claude, Gemini, or any other private service. Their complete production systems are not public, and they do not all use identical designs. We will study a representative modern language model, a decoder-only causal transformer. That architecture is common enough to explain the core mechanism, but every time a design choice can vary, I will say so. Decoder only means there is no separate text encoder preparing one representation and a separate text decoder consuming it. The same causal stack processes the known prefix and produces the distribution for what comes next. Before we zoom in, here is the full route. Your chat application first builds the actual model input. A tokenizer converts the text into token IDs. An embedding table converts each ID into a vector. The model combines token information with position information. A stack of transformer blocks repeatedly updates every vector. The last vector is projected into one score for every token in the vocabulary. Those scores become probabilities. A decoding rule selects one token. That token is appended to the sequence, and the model repeats the process. That is the map. Now let us walk through it without skipping the machinery. The user can see one message, but a chat product may construct a longer sequence before calling the model. The sequence may begin with a system instruction that describes the assistant's role or constraints. It may include earlier messages from the conversation. It includes the current user message. It may contain special markers that separate roles, such as system, user, assistant, or tool. It may end with a marker that tells the model an assistant response should begin here. If the product uses retrieval, it may insert passages from documents. If it uses tools, it may insert the result of a search, calculation, or database query. If it supports images or audio, other encoders and special input representations may also be involved. Those are product-level choices. They matter because the model can only condition on information that reaches it, but they are not the same thing as the core language model. For our example, imagine the product builds a sequence with 3 parts: a system instruction, the user request, and an assistant generation marker. The exact symbols vary by model. What matters is that the model receives one ordered sequence, not a set of floating chat bubbles. This distinction explains why the same visible user sentence can produce different answers in different products. The hidden system instruction may be different. The conversation history may be different. A retrieval system may have supplied different documents. The decoding settings may be different. The underlying model may also be different. When the sequence is ready, the model still cannot process the letters directly. It needs discrete identifiers. That is the tokenizer's job. The actual model call can also carry control tensors, such as an attention mask, position indices, and cache metadata. We will introduce each one when it becomes relevant. A tokenizer has two closely related parts. It has an algorithm that divides text into pieces, and it has a finite vocabulary that assigns an integer ID to each permitted piece. A token might be a whole common word or part of a longer one. Some include a leading space. Others are punctuation, 1 byte, or a short sequence of bytes. Depending on the tokenizer, Chinese text may be divided into characters, character groups, byte pieces, or other learned units. So the sentence, 1 token equals 1 word, is false. A token for every possible word would not solve the problem. Language keeps producing new names, technical terms, spelling variants, URLs, code, and combinations that were not placed in a fixed word list. A purely word-level vocabulary would either become enormous or fail on unfamiliar words. A character-only tokenizer would keep the vocabulary small, but common words would require long sequences. Longer sequences increase the amount of computation and consume more of the context window. Subword tokenization is a compromise. Frequent patterns can receive compact tokens, while uncommon strings can be broken into smaller pieces that are still in the vocabulary. There is no single tokenizer used by every LLM. Some use byte pair encoding variants. Some use unigram language model tokenization. Some work directly with bytes in part of the process. The details change, but the result needed by the model is the same: a sequence of integer token IDs. Consider a simplified byte pair encoding style tokenizer. It begins with small units and repeatedly merges adjacent units that occur together, often in its tokenizer training data. Frequent patterns become single vocabulary entries. Rare patterns remain split across several entries. This merge process trains the tokenizer, not the language model. Once the tokenizer is fixed, encoding a new sentence applies the learned vocabulary and merge rules. It does not retrain the tokenizer for every prompt. Suppose an illustrative tokenizer divides the phrase "unbelievable result" into pieces that look like "un," "believe," "able," and "result." Another tokenizer may split the same text differently. The spaces and pieces here are only an example. We should never present one split as universal unless we name and run a specific tokenizer. Our visible request might become a sequence like explain why the sky is blue in 1 sentence and a period. That looks word-like because the words are common. A real tokenizer could make a different split. The role markers and system instruction would also contribute tokens that the user did not type. The tokenizer vocabulary is sometimes described as the model's dictionary. That wording causes confusion. The vocabulary is a lookup between token pieces and integer IDs. For example, one entry may say that a particular text piece maps to ID 12,481. Another entry may map a punctuation mark to ID 13. Special tokens can mark the beginning of a sequence, the end of a sequence, or a message role. The vocabulary does not contain a definition of the token. It does not contain every fact associated with the text piece. The row for Paris does not contain a sentence saying, "Paris is the capital of France." It only tells the encoding and decoding system how to move between a text piece and an integer. The tokenizer vocabulary stores available token pieces and their IDs. The model parameters store learned numbers used in transformations. The current prompt supplies context. External tools may supply additional facts. These are different objects. Encoding maps text to token IDs. Decoding maps token IDs back to text pieces and then to visible text. Decoding is not the same as generating. The model generates or selects a token ID. The tokenizer then decodes that ID into text. A selected token may add a complete word, but it may also add only part of a word or a punctuation mark. That is one reason streaming text can sometimes appear in uneven chunks. For the model, the input now looks like a row of integers, T1, T2, T3, and so on, through Tn. Here, n is the number of input tokens. These integers are labels. Their numerical order has no semantic meaning. Token ID 8000 is not twice as meaningful as token ID 4000. We need to replace each discrete label with a learned vector. The model contains an embedding matrix. Call it E. If the tokenizer vocabulary contains V tokens and the model width is D, then the embedding matrix has shape, the vocabulary size, by the model width. There is one row for every token ID. Each row contains D learned numbers. When the input contains token ID I, the model selects row I from the embedding matrix. In code, this is an embedding lookup, X, at position I equals row I of the embedding matrix. You can also describe the same operation as matrix multiplication. Create a one-hot vector of length V, with a 1 at position I and zeros everywhere else. Multiply that one-hot vector by E. Every row is multiplied by 0 except row I, so the result is exactly the selected embedding row. The lookup is the efficient implementation. The one-hot multiplication is a useful mathematical explanation. Now apply that lookup to all n input tokens. Stack the selected vectors as rows. The result is a matrix. Call the resulting matrix X0. Its shape is n by d. The first dimension follows token positions. The second dimension is the model's internal feature width. We will follow one sequence and omit the batch dimension so the diagrams stay readable. A production input commonly groups several sequences, giving an activation tensor with a batch dimension such as B by N by D. For a toy model with 5 tokens and a width of 4, X0 has 5 rows and 4 columns. Real models use much larger widths, but the operation is the same. It is tempting to label one column animal, another color, and another grammar. That is usually misleading. The dimensions are learned together with the rest of the network. Useful information is distributed across many coordinates and combinations of coordinates. A direction or subspace can correlate with a feature, but the model was not built from a human-readable spreadsheet in which every column has one permanent meaning. An input embedding is also not the final meaning of a token. The same token ID begins with the same embedding row, but its representation changes as it passes through the transformer blocks. The token bank in riverbank and bank loan begins from the same token embedding if the tokenization is the same. Context-sensitive differences are created later. At this point, we have token vectors arranged in rows, but attention by itself needs a way to distinguish positions. Dog bites man and man bites dog contain similar token identities in a different order. The order changes the meaning. The original transformer added a position encoding to each token embedding. Other models learn position embeddings. Many modern LLMs use rotary position embeddings, usually called ROPE. In our representative model, ROPE acts later on the query and key vectors. It takes pairs of coordinates and rotates them by angles that depend on token position. Because queries and keys at different positions receive different rotations, their dot product can depend on relative position. You do not need the full trigonometric derivation to follow the rest of the model. The important point is precise. The model must encode order somewhere, and ROPE makes position affect the attention comparison between queries and keys. We now have enough to enter the transformer stack. A decoder-only transformer contains many blocks with the same overall structure, but different learned parameters. In the modern pre-norm form we will use, one block can be summarized with two equations. H equals X plus the attention update computed from normalized X. X next equals H plus the MLP update computed from normalized H. The first branch lets token positions exchange information through attention. The second branch transforms each position independently through a feed-forward network, usually called the MLP. The plus signs are residual connections. They keep the current representation on a direct path and add a learned update. The exact order varies across model families. The original transformer used a different normalization placement. Some modern models use layer norm. Others use RMSNorm. Some use dense MLPs. Others use mixture of experts layers. We will open a common modern dense block. It uses RMSNorm, self-attention, a residual addition, another RMSNorm, a SwiGLU-style MLP, and a second residual addition. Take one token vector x with d coordinates. RMSNorm first measures its root mean square. It squares each coordinate, averages those squares, adds a small epsilon, and takes the square root. Then it divides the vector by that scale and applies learned per coordinate gains. This operation helps keep the numerical scale controlled as information passes through many layers. RMSNorm is not deciding which earlier word matters. It is not adding a fact. It is normalizing a vector before the next learned transformation. The normalized matrix has the same shape as the input, n by d. Now, attention begins. For every token position, attention creates three different vectors: a query, a key, and a value. Starting from the normalized matrix X, the model multiplies by three learned weight matrices. Q equals X times WQ. K equals X times WK. V equals X times WV. Using row vector notation, X has n rows and width d. If there are h query heads, each with width dk, WQ maps width d to h times dk. The result is then reshaped into heads, each with n rows and width dk. Key and value projections follow the same idea. In grouped query attention, the model can use fewer key value heads than query heads. Here, V means the value matrix inside attention, not vocabulary size. On screen, vocabulary size will be written explicitly whenever both could appear. The three projections serve different roles. The query determines what pattern a position uses when comparing itself with other positions. The key determines how each position participates in those comparisons. The value carries the information that can be mixed into the output. That wording is an intuition, not a substitute for the calculation. The calculation is a dot product between a query and keys, followed by a weighted sum of values. It is called self-attention because the queries, keys, and values all come from the same sequence representation. In cross-attention, queries and key-value pairs can come from different sources. A standard decoder-only language model uses causal self-attention for its text sequence. Instead of performing one attention calculation across the entire width, ordinary multi-head attention divides the projected representation into several heads. Suppose the model has H heads. Each head works in a lower dimensional space, often with query and key width dk. A head receives its own projected Q, K, and V, or its own slice of a larger joint projection. Different heads have different learned projections, so they can compute different patterns of information mixing. We should not assume that each head has one stable English label. A head's behavior can depend on the layer, prompt, and interaction with the rest of the network. Some modern models use grouped query attention. They keep many query heads but share a smaller number of key and value heads. This can reduce the amount of key-value data stored during generation. It changes how heads share K and V, but it does not change the core sequence. Form queries, compare them with keys, and use the resulting weights to mix values. We will calculate one ordinary head first. Focus on one token position. Call its query Q at position I. Every allowed token position has a key, K, at position J. The model computes a dot product. The score for positions I and J is the dot product of the query at I and the key at J. A dot product multiplies matching coordinates and adds the products. If two projected vectors point in compatible directions, the result can be larger. Because the query and key projections were learned during training, the model learns which forms of compatibility are useful for reducing prediction error. For all token positions at once, the dot products form a matrix. In matrix form, that is Q times K transpose. If the sequence has n positions, this score matrix has shape n by n. Row I contains the scores used when position I reads from the other positions. Column J corresponds to the key at position J. The raw dot product tends to grow in magnitude when the vector dimension grows. Very large inputs can push softmax into regions with extremely sharp probabilities and small gradients. Scaled dot product attention divides the scores by the square root of the query key dimension. The scaled score matrix is QK transpose divided by the square root of DK. This is not a learned operation. It is a fixed scaling built into the attention formula. The model is supposed to predict the next token from earlier tokens. During training, it must not look at the answer sitting to its right. A causal mask blocks every future position. Before softmax, the model adds a mask that places a very large negative value, conceptually negative infinity, in each forbidden score cell. At position 4, the model may read positions 1 through 4, but not positions 5 or 6. At the last prompt position, it may read the entire prompt, because all prompt tokens are in its past or present. After softmax, the masked positions receive 0 probability. This produces the familiar, lower triangular attention pattern. The mask also enforces the probability structure of an autoregressive model. The probability of the whole sequence factors into one next token probability at each position, conditioned on the earlier tokens. Each token is modeled as conditional on the tokens before it. For each row, softmax exponentiates the allowed scaled scores and divides by their sum. The results are non-negative and add to 1. Call the resulting attention matrix A. A equals the softmax of the scaled score matrix plus the causal mask. Each row of A contains the mixing weights for one query position in one attention head. These are computational weights, not a guaranteed explanation of why the full model produced an answer. The final output depends on values, output projections, residual paths, MLPs, many layers, and the decoding process. Looking at one attention map can be informative, but it is not the same as reading the model's reasoning. Now multiply the attention matrix by the value matrix. O equals A times V. For one head, A has shape n by n. If that head's value matrix has shape n by dv, then O has shape n by dv. For one query position, this is a weighted sum of the allowed value vectors. For example, a position with weight 0.4 contributes 0.4 times its value vector. Another, with weight 0.1, contributes 0.1 times its value vector. Add the contributions, and you get the attention output for the query position. This is the central information mixing step. Queries and keys decide the weights. Values provide the content that is mixed. Let us make the operation concrete with invented two-dimensional vectors. These are not measurements from a real model. Suppose the current query is the vector 1, 1. It compares with 3 key vectors. Key 1 is the vector 1, 0. Key 2 is the vector 0, 2. Key 3 is the vector 1, 1. The dot products are 1, 2, and 2. Because dk is 2, divide each score by the square root of 2. The scaled scores are approximately 0.707, 1.414, and 1.414. Softmax converts those values into weights of approximately 0.2, 0.4, and 0.4. Now suppose value 1 is the vector 1, 0. Value 2 is the vector 0, 1. And value 3 is the vector 1, 1. The weighted sum is the following expression. 0.2 times the vector 1, 0, plus 0.4 times the vector 0, 1, plus 0.4 times the vector 1, 1. That gives an output close to the vector 0.6, 0.8. The output is not a selected earlier token. It is a new vector formed by mixing value vectors. In a real head, the dimensions are larger. The query and key values were produced by learned projections. Position information affects the comparison, and the calculation runs for many positions in parallel, but the mathematical sequence is the same. Now, return to rope. Before the query key dot products, rope rotates paired coordinates in queries and keys according to their positions. Imagine two-dimensional arrows. Rotating both by position-dependent angles changes the angle between the query at position I and the key at position J. The dot product can therefore reflect not only token content, but also the relative distance and ordering between positions. Rope does not append a plain position number to every token. It transforms the geometry used in attention. Other models encode position differently, so this is one of the architecture choices we must label. Every attention head produces an output for every token position. The model concatenates the head outputs and multiplies by another learned matrix, usually called WO, to return to the model width D. If the input to the attention branch has shape n by d, the combined attention update, also has shape n by d. Matching shapes are important because the update will be added to the residual stream. The attention branch does not replace the entire representation. The model adds its output to the block input, h equals x plus the attention update, computed from normalized x. The residual path lets information flow through the network, while each branch writes an update. It also helps optimization in a deep stack, because gradients have more direct routes through the network. At this point, token positions have exchanged information through attention. Next, the MLP transforms each position separately. The MLP is sometimes called the feed-forward network. The same learned function is applied independently to every token row. Unlike attention, this operation does not mix different sequence positions directly. A simple transformer feed-forward network projects a vector into a wider hidden dimension, applies a nonlinear activation, and then projects the result back to the model width. Many modern LLMs use a gated version such as SwiGLU. One common form is, on screen, the SwiGLU equation shows the activated gate multiplied element by element with the up projection, followed by the down projection. With row vector notation, W gate and W up map from D to a wider dimension DFF, so each can have shape D by DFF. W down maps the gated result back and can have shape DFF by D. Implementations may store transposed layouts, but the input-output dimensions are the same. Read it from the inside out. First, two learned projections create two wider vectors. One passes through the SwiGLU activation and acts as a gate. The gate is multiplied element by element with the other projected vector. A final learned projection brings the result back down to width D. The wider intermediate space gives the model more capacity to transform features. The nonlinear gate makes the result more expressive than one matrix multiplication. The exact formula varies. Some models use ReLU or GELU. Some include bias terms. Some replace one dense MLP with a mixture of experts layer that routes tokens through selected expert networks. The main point remains. After attention mixes information across positions, the MLP performs a learned nonlinear transformation at each position. Before the MLP, our specimen applies RMSNorm again. After the MLP, the model adds another residual update. X next equals H plus the MLP update, computed from normalized H. One transformer block is complete. The output matrix keeps the same outer shape, N by D. That can make it look as though nothing changed. In fact, the values inside every row have changed. The initial row for a token came from an embedding lookup. After one block, it contains a residual representation plus information mixed from allowed positions and transformed by the MLP. The next block receives that new matrix and performs new learned projections with different parameters. Repeat this across dozens or more blocks, and the representation at each position becomes deeply dependent on its context. We should be careful with the usual story that early layers learn spelling, middle layers learn grammar, and late layers learn reasoning. Researchers can find patterns and circuits in particular models, but real representations are distributed and overlapping. There is no universal rule that assigns one clean human concept to every layer or neuron. Every layer applies learned attention and nonlinear transformations to the current representations. Training shapes those transformations so that the final representations help predict the next token. The model produces a hidden vector for every input position. For next token generation, the key row is the row at the final current position. Because of causal attention, that position can depend on the entire available prefix. Its final hidden vector is the model's current numerical representation for predicting what should come after the sequence. It is not a sentence written in a secret internal language. It is a vector of learned features. We now need to turn that vector into one score for every possible next token. Many models apply one final normalization to the last hidden vector. Then they multiply it by an output matrix, sometimes called the unembedding matrix. Z equals the last hidden vector times the unembedding matrix. With our row vector convention, the last hidden vector has width d. WU maps those d coordinates to the vocabulary size. So Z contains one logit for every vocabulary token. The result Z is the logit vector. There is one logit for every token in the vocabulary. Some models tie the output matrix to the input embedding matrix, meaning they share parameters in a particular orientation. Other models keep them separate. Weight tying is a design choice, not a requirement for the mechanism. A logit is not yet a probability. It is an unnormalized score. A logit can be negative. The logits do not have to add to 1. Softmax converts the logits into normalized probabilities. For token I, exponentiate logit zi and divide by the sum across every candidate. Larger logits receive larger probabilities, and all probabilities add to 1. For our request, the distribution may assign relatively high probability to token pieces that could begin a concise explanation. The exact candidates depend on the model, the complete serialized context, and the tokenizer. Any probability bars shown in this lesson are illustrative unless we run a named open model and record its actual outputs. This distribution is the model's direct output for the next position. The model does not output a complete paragraph in one matrix operation. It outputs scores, or probabilities after softmax, for the next token. A decoder can divide logits by a temperature T before softmax. For token I, divide logit Zi by temperature T before exponentiating and normalizing. A temperature below 1 makes differences between logits more pronounced, producing a sharper distribution. A temperature above 1 flattens the distribution and gives lower scoring tokens more chance. Temperature does not teach the model new facts. It does not rewrite the weights. It only changes how the existing next token scores are converted into a choice distribution. The simplest decoder is greedy decoding. It chooses the token with the highest score every time. Sampling draws a token from a probability distribution instead. This introduces randomness into token selection, even when the model, prompt, and logits are the same. Top K sampling keeps only the K highest probability candidates, removes the rest, renormalizes, and samples from the survivors. Top P, or nucleus sampling, sorts candidates from highest to lowest probability and keeps the smallest set whose cumulative probability reaches a chosen threshold P. The size of that set can change from one decoding step to the next. Production systems can add repetition penalties, token bans, grammar constraints, safety controls, or proprietary decoding logic. So, the model chose. This token often compresses 2 operations. The model produced logits, and the decoding system selected a token under a set of rules. Suppose the selected token decodes to the beginning of the word sunlight. That token ID is appended to the sequence. The answer is not finished. The model must now predict what comes after that new token. The sequence now contains all prompt tokens, plus the first generated token. The model runs again, and produces a new distribution for the next position. The decoder selects another token. That token is appended. The cycle repeats. Context becomes logits. A decoder selects one token. The token is appended, producing a new context. This is autoregressive generation. Every new choice becomes part of the input condition for the next choice. That dependency is why the output tokens cannot all be generated independently in one parallel step. The probability for token number 10 depends on which tokens were actually selected in positions 1 through 9. The process stops when the decoder selects an end-of-sequence token. The product recognizes a stop sequence. The response reaches a maximum length, or another control interrupts generation. Modern inference engines separate the work into two phases. During prefill, the model processes the prompt tokens. The causal mask still applies, but the hardware can compute the representations for all prompt positions in parallel because every prompt token is already known. During decode, the engine generates one new token position at a time. Each step depends on the token selected in the previous step. This helps explain a behavior users can feel. A long prompt can increase the delay before the first token because prefill has more input to process. Once generation begins, tokens arrive at a different rate because decode is sequential. The exact latency depends on hardware, batching, model architecture, context length, software kernels, and server load. But the prefill decode distinction is fundamental to autoregressive serving. A naive implementation could run the entire growing sequence through every layer again after each new token. That would repeat a great deal of work. Look back at one attention layer. Earlier tokens already produced key and value vectors in that layer. In a causal model, appending a future token does not change what an earlier token was allowed to attend to when its stored key and value were computed. The inference engine can save those keys and values in a KV cache. At the next decoding step, the new token produces a new query, key, and value in each layer. Its query compares with the cached keys from earlier positions plus the new key. The attention weights mix the cached values plus the new value. The engine then appends the new key and value to the cache. This avoids recomputing keys and values for the entire prefix at every step. The new position needs to compare its new query with earlier keys and read earlier values. It does not need the old queries to calculate the new position's attention output, so inference engines do not usually cache every old query. The cache is maintained separately for every relevant layer and sequence. It can consume substantial memory, especially with long contexts, large batches, many layers, and many key value heads. Grouped query attention, quantized caches, offloading, paging, sliding window attention, and other techniques address different parts of that cost. The KV cache makes decoding faster, but it does not make the entire response parallel. Each new token still waits for the token before it. After each selection, the token ID is decoded into text. The product can stream that text to the interface while the next token is being computed. Because tokens are text pieces rather than guaranteed whole words, a product may buffer pieces before displaying them. It may also perform moderation or formatting. What the user sees is therefore the output of both model decoding and product behavior. We have now explained inference. Fixed, learned parameters transform the current token sequence into next token logits, and the serving system repeats that process efficiently. The matrices did not begin with useful values. Training produced them. Take a tokenized training sequence. The cat sat on the mat. The model receives each prefix and should assign high probability to the token that actually followed it. After the target is cat. After the cat, the target is sat. After the cat sat, the target is on. During training, these predictions do not have to be processed one prefix at a time. Put the known sequence into one causal forward pass. The mask prevents each position from seeing future targets, while the hardware computes predictions for all positions in parallel. The inputs and targets are the same sequence shifted by one position. Input positions. The cat sat on the target positions. Cat sat on the mat. At every position, the model outputs a distribution over the entire vocabulary. For one position, look at the probability assigned to the correct next token. If the model assigned the correct token a probability of 0.8, the loss is lower. If it assigned a probability of 0.001, the loss is much higher. The negative log likelihood objective can be written as the loss is the negative sum across positions of the log probability assigned to each correct next token. Here, theta represents all trainable parameters: embeddings, query key value projections, output projections, MLP weights, normalization gains, the final output matrix, and any other learned components. The logarithm matters because probability errors combine cleanly across token positions, and because assigning extremely low probability to the correct answer is penalized strongly. The loss compresses many next token errors into a number the optimizer can reduce. The forward pass produced logits, probabilities, and a loss. Backpropagation applies the chain rule in reverse through the computation graph. It calculates a gradient for every trainable parameter. The gradient measures how a small change in that parameter would change the loss. The gradient travels backward through the output projection, the final normalization, every MLP, every attention projection, every residual path, and the embedding table. An optimizer uses those gradients to update the parameters. The update for a weight can be simplified as moving it a small amount in a direction expected to reduce future loss, although practical optimizers maintain additional statistics and use more detailed update rules. One batch does not create a language model. Training repeats across enormous numbers of token positions. The same parameter participates in many contexts. Useful statistical structure accumulates in distributed form across the network. This is where the matrices come from. A person chooses the architecture and training procedure, but a person does not type billions of useful matrix entries by hand. Optimization adjusts them from data. Predicting the next token across varied text rewards many useful internal distinctions. To continue grammar correctly, the model benefits from representing syntactic patterns. To continue a technical explanation, it benefits from representing relationships among concepts and the structure of explanations. To continue code, it benefits from tracking names, delimiters, types, and common algorithms. To continue a dialogue, it benefits from using instructions and earlier turns. These abilities are not inserted as separate apps inside the model. They arise from parameters that support accurate prediction across many contexts, followed by post-training that shapes how the model responds to users. We should not turn that statement into a stronger claim than the evidence supports. Predictive competence is not proof that the model experiences meaning as a person does, and strong average performance does not guarantee correctness on a particular prompt. Next token pre-training creates a base model that can continue text, A chat assistant usually undergoes additional training. Supervised instruction tuning uses examples of prompts and desired responses. Preference-based methods compare possible responses and adjust behavior toward selected preferences. Safety training and specialized data can change which responses are likely in particular situations. The exact post-training recipe differs by organization and model. Some details are public, others are not. After post-training, inference still uses the same basic mechanism we followed. Serialize context, tokenize, run fixed parameters forward, produce logits, and decode tokens autoregressively. Post-training changes the learned parameters and sometimes the surrounding controls. It does not replace matrix computation with a hidden human-written answer engine. When you send a message, the current context changes. Activations change. The KV cache changes as tokens are processed. The generated response becomes new context if the conversation continues. But in ordinary inference, the base model parameters stay fixed. This is the difference between learning in the training sense and adapting to context. A model can follow a pattern demonstrated in the prompt without running backpropagation or updating its base weights. That behavior is often called in-context learning. Some products save user information, build external memory, or later use logs in a separate training process. Those are product and data policy choices. They should not be confused with the forward pass of the language model. We can now answer this precisely. The tokenizer vocabulary is a real, finite dictionary, from token pieces to IDs. It supports encoding and decoding. The embedding matrix gives each token ID a learned starting vector. The model's broader statistical knowledge is not stored as readable definitions beside those token IDs. It is distributed across embeddings, attention projections, MLP weights, normalization parameters, output projections, and the interactions among them. The current prompt is stored separately as token IDs and runtime activations. The KV cache stores per-layer keys and values for the current sequence. Retrieved documents or tool results come from outside the base model. Calling all 5 of these memory hides more than it explains. The direct training objective rewards probability assigned to observed next tokens. The inference mechanism produces likely continuations under the learned distribution and current context. Neither operation automatically verifies a claim against a trusted source, a calculator, a live database, or the physical world. The model can produce an accurate sentence because the learned patterns and context support it. It can also produce a plausible but false sentence because that sequence fits locally. The data were incomplete, the prompt was ambiguous, or the required information was not represented reliably. Retrieval can provide sources. Tools can calculate or execute code. Tests can check outputs. A human can inspect evidence. Those verification steps strengthen the complete system, but they are not the same operation as next token prediction. For fixed weights, fixed input tensors, and fixed numerical execution, the forward pass produces logits through deterministic mathematical operations. Sampling can then add randomness to token selection. In practice, server implementations, numerical precision, batching, hidden product context, model updates, and decoding settings can also affect reproducibility. So 2 answers can differ for several reasons. The model is random, is too vague. The model computes a distribution. The decoder may sample from it. The surrounding product may also change the actual input or rules. Let us follow our request one last time. You type, "Explain why the sky is blue" in one sentence. The chat product combines that request with role markers, system instructions, and any permitted context. The tokenizer splits the serialized text into pieces and maps them to token IDs. The embedding table maps each ID to a learned vector. Position information enters the attention computation. In every transformer block, normalization controls scale. Query key dot products produce compatibility scores. The causal mask blocks future positions. Softmax produces mixing weights. Those weights combine value vectors. Multiple heads are joined and added to the residual stream. An MLP transforms every position and adds another update. After the final block, the hidden vector at the last position is projected into one logit per vocabulary token. Softmax and decoding rules turn those logits into a selected next token. The tokenizer decodes it into text. The token is appended, and the loop repeats, using a KV cache to reuse earlier keys and values. During training, the same general network predicted next tokens across many sequences. Cross-entropy measured its errors. Backpropagation computed gradients. An optimizer adjusted the matrices. Post-training then shaped the base predictor into a more useful assistant. That is what sits between pressing send and seeing the first token. The short phrase, predicts the next token, is not wrong. It is the final line of a long computation. Text becomes IDs. IDs become vectors. Vectors exchange and transform information through learned matrices. And one final vector becomes a distribution over a finite vocabulary. Once you can trace that route, the model is still complex, but it is no longer a black box with one label. It is a sequence of inspectable mathematical operations, each with an input, an output, and a specific job.